everyone, welcome! This educational channel expounds topics in mathematics, civil engineering, and professional education subjects. This channel aims to simplify the lessons, and I am its founder, Bert, a Filipino licensed teacher and engineer. Thank you for watching.
Hello everybody! I will discuss the linear equations of order 1. This topic will be discussed in 2 videos, and this is the first video. As shown in the list, the linear equation of order 1 is the 4th lesson in the solution of some order differential equation. To understand our lesson, you should have a good background on lesson 1 to lesson 3, namely, separation of variables, equation with homogeneous coefficients, and exact equations. If you did not yet study these topics, you can watch our videos on these topics. Well, we will now discuss the linear equations of order 1. In our previous lesson, we found that solving exact differential equation is very easy, right? And do you know that we can convert an integrand into an exact differential equation? We can do this by multiplying the integrand by a certain factor, which is known as an integrating factor. For example, we are going to multiply our integrand here with the integrating factor, that is dy plus y over x dx multiplied by x. The product now, dy multiplied by x is x dy plus our x here multiplied by x here, that is cancelled, so we have here y dx. And this expression is an exact. You can check this with the solutions we have presented in our previous discussion. But anyway, the answer for this exact is x, the integrating factor, and the integral of dy, which is y. You notice, if you are going to get the derivative or differential for xy, the answer is x dy plus y dx. So, the solution is xy. As shown, our integrand is converted into an exact differential equation. Then, let's have another example. In our second example, the integrand is dy plus 2xy dx, and the integrating factor is e raised to x squared. Now, we are going to find the product of this expression. So we have here dy plus 2xy dx, then multiply by e raised to x squared. The product is multiply this dy and this e raised to x squared. So we have here e raised to x squared dx. And then for this second term, we have 2xy, then e raised to x squared dx. This product is exact, and the solution for this is the integrating factor, and pair that one with the integral of dy, which is y. If you are going to get the differential for this solution, you will arrive with this product. So therefore, this is an exact. But anyway, for this solution, we will have to review the product formula. As I recall, the differential for uv is equal to u dv plus v du, where our u is e raised to x squared and our v is y. Then the differential of e raised to x squared y is equivalent to our u, which is e raised to x squared. Then the dv is the differential of y, which is equivalent to dy, plus our v is y, and the differential of u is e raised to x squared, and derivative for x squared is 2x. As shown, the differential of e raised to x squared y is equal to the product. Therefore, we're able to convert the integrand into an exact differential equation. Our third example, the integrand is dx plus 3x over y dy, and the integrating factor is y cubed. Our third example is different from the previous two examples, since the first term in our third example is dx, and in the previous, the first term is dy. Anyway, we are going now to follow the procedure. We are now going to multiply the integrand by the integrating factor. So we have here dx plus 3x over y dy, then multiply by y cubed. Then dx multiplied by y cubed is y cubed dx, plus y cubed divided y is y squared. So the answer here is 3x y squared dy. This is again an exact, and the solution for this is the integrating factor, that is y cubed, and the integral of dx, that is x. So our solution is x y cubed. Now let's have a detailed solution in solving the differential for this xy cube. The differential for that xy cube using the product formula is u dv plus v du, where our u is x and our v is the other factor, the y cube. Then substitute, our u is x, the dv here is 3y squared dy, plus our v is y cubed, and our du is dx. Then simplify for this, 3x y squared dy plus y cubed dx. As shown, our expression here is equivalent to the product of integrand and the integrating factor. Therefore, we're able to convert the integrand into an exact expression. And take note, our solution here, this is the integral of x. These are the three integrands that we converted into exact equations. From these examples, we have two prime questions. First, how to determine these integrating factors. Second, are all integrands can be converted into an exact? For the second question, the answer is no. Not all integrands can be converted. Nevertheless, one of the integrands that is convertible is a part of the linear equations of order 1. And this is our lesson today. Specifically, our learning outcomes at the end of the lessons, the students will be able to identify an equation either linear or not. Second, solve linear equations of order 1. The standard form for the linear differential equation in y of order 1 is dy over dx plus pxy equals qx. Or, the dy over dx can be written into y prime, wherein in this equation, px and qx are functions. In this form, please note three important things. First, the first term here in the left side of the equation contains only the dy over dx or y prime, no other coefficients. Second, the second term contains the variable y and a functions of x. Again, it contains a variable y and a function of x. The variable y should only be raised to the first power if the exponent is not 1, such as square and cube, the equation is not linear. Then, moreover, px is a function of x, which is a polynomial. For example, px can be equal to 3x, or it can be equal to x squared minus 7x. Third, the right side of the equation should also be a polynomial of x, denoted by qx. Again, our qx can be similar to our px. It should be a polynomial of x. Now, let us relate this standard form to our previous example of integrands. The first example is dy plus y over x dx. To come up with a standard form, we multiply these two terms by 1 over dx. The product is dy over dx plus cancel dx, we have y over x. But I have to write 1 over x separately from the variable y. As you can see, these two terms constitute the left side of the standard linear equation. And to make this into a complete linear equation, there should be a function of x at the right side. For instance, we can add here 3x, just for an example. From this equation, our px here is equal to 1 over x, and our qx is equal to 3x. Our second integrand is similar to the first one, specifically dy plus 2xy dx. Again, we can multiply this one by 1 over dx. The product is dy over dx plus cancel dx. So we have here the function of x, 2x, and y. Similar to the previous, what is lacking here is the qx. Maybe we can put here 7x squared minus 3x. If this is our qx, then we have now our complete linear differential equation, from which our values are px equals to 2x and our qx is equal to 7x squared minus 3x. Now we are going to solve a linear differential equation. Example 1. Solve the equation dy over dx plus y over x is equal to 3x. Our step 1, we're going to write the equation into the standard form. So we have here dy over dx plus our px here, that is 1 over x, then y is equal to 3x, where our px is equivalent to 1 over x. Then step number 2, determine the integrating factor. The formula is v equals e raised to integral of t dx. So we have here v is equal to e, integral of p is 1 over x, then dx. Then it is equivalent to e, and integral of dx over x is ln of x. Then simplify using the ln property, then that is equal to x. Then step 3, we are going to multiply the equation by the integrating factor. We can use either this form or the given equation. And this time, I'm going to use the given equation. We have dy over dx plus y over x is equal to 3x. Then multiply this by our integrating factor x. So the equation here is x dy over dx plus cancel x, so we have y is equal to 3x squared. After this, we are going to integrate. You notice in integrating the equation, we still need to transpose dx to the numerator. So we're still going to multiply this by dx. So we have here x dy plus y dx is equal to 3x squared dx. Then we are going to integrate the left side and integrate the right side. As I have mentioned, this x dy plus y dx is an exact, and the solution for that is simply the integrating factor, which is x, and the integral of dy, which is y. And this is now equals to integral of 3x squared dx is 3, then integral of x squared is x cubed over 3 plus constant. Then simplify, we have xy is equal to cancel 3, we have x cubed plus c. And this is our final answer. Example 2. Solve the equation dy plus 2x times y minus 1 dx equals to 0. Step 1. Write the equation into the standard form. I'm going to simplify this one. We have dy plus 2xy minus 2x dx is equal to 0. Then I'm going to expand this term. Dy plus 2xy dx minus 2x dx is equal to 0. Then we are going to multiply this by 1 over dx. Remember, we are going to come up with this standard form. So we have now dy over dx plus, this is cancelled, so we have here 2xy, and dx here is also cancelled, that is minus 2x is equal to 0. Then, writing this into standard form, you notice at the right side is only the function of x. So, we are going to transfer negative 2x here to the right side. So, our standard form is dy over dx plus 2xy is equal to 2x. In this standard form, we can now identify our value for the function px, and that is equivalent to 2 x. With this value for px, we can now determine our value for v. V here is equal to e raised to integral of p dx. I'm going to substitute here the value of our p, which is 2x, then dx, equals, then e, integral of 2x dx is equivalent to 2x squared over 2, then equals, cancel this one, so you have now e x squared. Therefore, our integrating factor is e raised to x squared. For our step 3, we are going to multiply the equation by the integrating factor. I'm going to use now the standard form. This is our standard form, this one. So we have dy over dx plus 2xy is equal to 2x. Multiply by our integrating factor, which is e raised to x squared. At the same time, we're going to multiply this by dx so that the dx will become numerator. So we have here e x squared, then cancel, so we have dy plus multiply 2xy and this one, so you have 2xy e x squared dx is equal to 2x, then e x squared dx. After that, we are going to integrate the left side and also the right side. So we have here integral. I will just copy the terms. We have e x squared dy plus 2xy e raised to x squared dx. On the right side, I'm going to write the constant before the sign of integration. Then we have x e x squared dx. This left side is already an exact, and the answer for this is the integrating factor, which is e raised to x squared and the integral of dy. This is y. Then equals, then we are going now to integrate to integral of x e raised to x squared dx. Recall, we are going to use here the formula integral of e u du. And the answer for this is e u plus constant, where our u here is equivalent to x squared. Then the du is 2x dx. So this is now integral of our e, then u is x squared, then the du is 2x dx. And it should be equal to e, your u is x squared plus c. You notice this expression is exactly equivalent to this one. That means there is no correction factor. So the answer here is e x squared, then plus the constant. This is our final answer. Hello everyone, this is the end of our first video on the linear equations of order 1. For the continuation, you may proceed to the second video on this topic.